electric energy and magnetic energy actually shares many features, like at least in terms of mathematical formulation, right? So electric energy, like parallel capacitor, stores charge, right? That is proportional to the voltage applied between the plates. And here, magnetic energy, you store magnetic flux, and then that is linearly proportional to current that is running through the wire. And the coefficients are here. In the electric case, it's capacitance. In magnetic case, it's inductance. And both of these quantities only depends on the structure, right? It doesn't depend on like how much of voltage you applied. And here also how much of a current you run doesn't actually affect the amount of L, the inductance. And then electric energy is 1/2 CV squared, and magnetic energy is 1/2 Li squared. And this can be also calculated by integrating D dot E or H dot B over entire space. Again, keep in mind that this holds only when you run this integral over entire space, right? And you know why. Like in the derivation step, you made this surface integral to be 0, and then that approximation is only possible when your integration volume is infinitely large. Okay, and then we talked about the exceptions to flux rule. So the first exception was the disk generator, as I showed you before. And in this case, it is, so why this is difficult is because the current can flow anywhere on the disk. And so it's difficult to define what is circuit area, right? So one way to obtain, resolve this problem is to going back to the fundamental microscopic force. So if you calculate the microscopic Lorentz force applied to a unit charge on the disk, then you can get the F, this microscopic force, and then by integrating it along the path, you can obtain the electromotive force, right? So that's one way to figure to resolve the situation. And the other way is this: you define the flux linkage, which is not exactly B dot ds, because B dot ds in this case S is ill-defined. There's no definition of surface area in this case. Not everyone agrees upon like single definition. So in this case, what we do is we define like what is called flux linkage, and then we assume that the circuit area actually changes from this to this as time goes by. And so this amount has been increased, right? And then that is the change of circuit area, and that's kind of how we define the flux linkage. So again, the flux linkage is defined by using the area swept by a hypothetical line across the disk from the brush to the exile. So it's like this. We draw a hypothetical line here, and then the disk just spins, and then let's say time delta t has been spent, then this amount of area is going to be swept by this hypothetical line. So that's how you define like a surface area difference in flux linkage. Okay, so this is one way to resolve the problem. So do we have any questions so far? Anything? Okay, so if there's nothing, then I'll move on to another case, another exception to flux rule. So in this case, we deal with a coaxial cable. So coaxial cable looks like this. And then inner conductor has non-zero thickness, like it's kind of filled cylinder. And then the current flows with a uniform current density. So in this case too, it's difficult to define what is circuit area, right? If our cylinder, inner cylinder was like cylindrical shell instead of a solid cylinder, then there might be no problem, because here now you have zero thickness inside and outside, so you can define your circuit area like this, right? Depending on where it's connected. But if somebody asks you what's the self-inductance per unit length, then there's no problem defining this distance, right? Excuse me. And yeah, but even in this case, there's no problem in calculating magnetic field, right? It's easy thing, just applying Ampere's law. So one way to resolve this problem is evaluating energy first. So first evaluate magnetic energy, which is 1/2 h dot b over all space. And this should be equal to 1/2 Li squared, right? So by evaluating energy per unit length, then we can easily evaluate the inductance, self-inductance per unit length. No problem, because we know H and B everywhere. It's easy calculation, right? But isn't there any way to somehow use the flux linkage, or is there any way to somehow define a magnetic flux in this case? There is a way to do it, and here's the way. So now let's think about the situation. Situation is like, this is top view, right? So this is cross-sectional view. And then if you look at the same problem side view, this is side view. And then here you have current going up, and then here you have current going down. In the middle, there's nothing, right? And the magnetic field is actually like having this form. So what is it? So it's like, and also, of course, even in the cylinder, there's some magnetic field, right? So this is the situation. So now, how do we deal with it? So what we want to try is to divide the inner cylinder into many, many pieces. Okay, like here, we divide the cylinder into infinitely many cylindrical shells with with thickness d rho. Okay, so no problem doing that. So we have infinitely many cylinders here, cylindrical shells. And then for each cylindrical shell, there's no problem defining surface area, right? Because we can clearly define the distance between the cylinder and the outer cylinder, right? So if we calculate the flux, magnetic flux, for each of these smaller cylindrical shell with radius rho prime, we can do this calculation, right? So from rho prime to A. So rho prime is smaller than A because it's shell inside. So, and then evaluate BDL, I mean BDS. And then here from A to B, magnetic field amount is fixed. I mean, it does not depend on this rho prime anymore. And then you can calculate this. So magnetic flux passing through this area can be calculated by psi. But the thing is, if you think about the current amount, the current passing through this small cylindrical shell is not I, right? I is the total current. So the current passing through a cylindrical shell, of course, is pi a squared and then 2 pi rho prime d rho prime, right? So 2 pi rho prime is the circumference of this cylindrical shell. D rho prime is the thickness. So if you multiply those, you get a small infinitesimal area of this shell. And then if you divide it by pi a squared, the total area, then you get di over I. The contribution of the current due to this small cylindrical shell, right? And that's how you define d lambda. So like infinitesimal flux linkage associated with this small cylindrical shell with radius rho prime. So the only step left is you just integrate this d lambda from rho prime 0 to a. And then you get the total flux linkage, right? And if you do this calculation and then divide it by I and L, L is just a length, like just random length you chose. And you get the same answer, exactly same answer that you got in the previous slide. So is there any question related with this? Is this clear enough? Or you just want to know whether you actually got the point? Or you just completely lost, so you're not asking any question? Okay, how many of you got the point? Please raise your hand, please. If you got the point, please raise your hand. Okay. Okay, if you got the point, please keep raising your hand. Okay. Okay, not that many people. So then what's happening? Okay, you can put down your hand. What's happening with others? Just please let me know which point is confusing. I just want to make sure that everyone understands this. So the main problem in these two examples were like the current is flowing through some area, right? Not just a line, so that it's difficult to define what the area of a circuit, and so it's difficult to define magnetic flux, right? So that's the main problem. And in order to solve this problem, here what we did is we divide a volume current into many, infinitely many surface currents, right? And then for that surface current, individual surface current, the definition for magnetic flux becomes more clear, right? So that we define that way and then take integration in order to get the total flux. So that's this approach, the approach that we did. But apparently, I guess my explanation was not clear enough so that many of you actually seems like couldn't follow. So please ask me if there's any question. Okay, well, So just leave the question if in the chat box if there's any. I always encourage you to leave the question. Okay. So let's move on then. So what we are gonna do from now on is we are gonna explain about the final missing piece. Okay, so Park Se-won asks the question. Park Se-won asks, so by dividing the cylinder to infinitely many shells, we are closer to be able to approach by using the flux method. Yes, yes. So by dividing this into many cylinders, we are, able to use the flux method, even apply the flux method in this problem. Yes, that is true. And then, but what I can tell you is that, all these things like dividing things into infinitely many pieces, and then sometimes we define the flux like as if the area swept by a hypothetical line. All these things are sometimes it's difficult to apply. So if possible, I always recommend you to go back to the first principle, like calculate magnetic force, microscopic force, and then integrate. I mean, this is clear, right? And then there's no way that this is wrong. And then here too, energy, the relation between energy and the inductance is also clear. So there's no ambiguation here. Okay, so I actually recommend this way is better than actually dealing with complicated definition of flux linkage. But I'm just telling you that this is possible. Okay. So going back to the final piece of displacement current. So we know that Ampere's law was curl of H is JF. Okay. And then Maxwell's contribution on Maxwell's equations is actually lies on the Ampere's law. So Ampere's law is actually not complete. And that is obvious if you look at here. If you look at the situation, so let's assume that you have current I flowing here, which means you have positive charges are piling up on the upper plate of the capacitor, and then negative charges are piling up in the opposite side, and then current is keep flowing. And as time goes by, the amount of positive charge and negative charge will keep increases, right? So this is the situation. And now, what Ampere's law says is that if you do a line integration for this given path, this must be equal to the current enclosed by this path. And that applies very well in this, if you take the surface like this. But actually, if you take the surface like this, surface passing through the gap between the capacitor, then there's no current actually flowing between the capacitor. So the enclosed current becomes zero. Okay, which is a problem because Ampere's law only talks about the line integral, and then there's there's no restriction in terms of choosing the surface, as long as that surface has a boundary defined by this line. So choosing this surface is completely fine actually, but somehow leads to a very strange conclusion. So we have to add one more term, right? We have, at least we need some correction. And that the correction they made was this. So if you define if you add Ampere's law to dt, okay, which is sometimes called displacement current, because this D field is called displacement field. So dt, then here in this case, you don't have any D field you can measure here at this point, but you can D field change you can measure, but there's a current. But here inside the capacitor gap, there's no actual current, but D field changes as a function of time. Why? Because there is charges piling up, and then as time goes by, the amount of charge increases, which means the electric field between this two capacitor increases as a function of time. So if you take the time derivative, you get non-zero term. And that is actually exactly the same as I. So in any case, here and there, you get the total current of I. So this is a real current, and this is called a displacement current. But in any case, there's, the contradiction has been resolved. And then we call this as a dt term as a displacement current density, JD. Okay, and it seems more reasonable to do this, because if you look at the full equation, now this is the full Maxwell's equation. And it seems more reasonable to have dt term here, because there is dB dt here. So time derivative of the B field induces E field in a curly way. And similarly, time derivative of E field or D field causes H field or B field in a curly way, right? And then if you look at the differential form, divergence of D is rho F. This is exactly same as the electrostatics. And then here, divergence of B is 0. So this is full Maxwell's equation. And then this is constitute equations, like the relation between E and D, and then H and B. Okay? So Maxwell's contribution on these Maxwell's equations actually is he unified all these equations into one mathematical system. But like in terms of physical contribution, he added this term. Okay. Other than that, all these other things has been discovered by other people. But he kind of summarized everything into one nice form. So now you are looking at the Maxwell's equation again. Probably this is the second time you are looking at the full Maxwell's equations. And the first time was the very first time. The very first time before we learn about mathematics. When I try to motivate you why you need to learn mathematics, I just showed you these Maxwell's equations. So compared to that time, I hope you feel very differently when you look at Maxwell's equations, right? Now, I hope you kind of get some sense what these equations mean. And then, like again, divergence is about the field generation, right? So this means if you have a charge, then electric field is generating in diverging manner. That's the meaning of this first equation. Second equation means there's no magnetic charge, no magnetic monopole, so that magnetic field never generated in a diverging manner, in like just from a monopole. And this means the time derivative of B field creates electric field in rotating manner, right? So if this was a B field direction, and then if it changes as a function of time, it can create E field in a rotating manner. And similar thing happens to H field can be created by current or changing D field, right? Both of these can cause H field to be generated. Okay, and this of course is just an associated integral form. Everything's good, right? So you at least now know what are the Maxwell's equations. And that's all about electromagnetism, actually, just understanding Maxwell's equation. And from now on, what we are gonna do is just applying the Maxwell's equations to describe like meaningful situations. But before then, boundary condition is always important. And boundary conditions are basically the same. Like, as I said, as we learned, surface normal component of D field can be discontinuous by surface free charge amount. But surface parallel E field must be continuous. And then surface normal B field must be continuous. And then surface parallel H field can be discontinuous by surface current amount, surface free current amount. Okay, so these are what we already knew from our previous discussions. Okay. Okay, so 4 Maxwell's equations and 4 boundary conditions. That's basically everything you need to keep in mind. And that's everything about electromagnetism. So the final topic we want to cover, before we actually move on to the next section, next chapter, is time varying potentials. This is not a necessary thing to know, but I think it's good to it's an interesting topic. So in static electromagnetic field, electromagnetism, we knew that curl of E was 0, electrostatics. And because of that, electric field can be expressed as a gradient of a scalar potential. So that's electrostatics only, right? And then magnetic field, divergence of B was 0. And this allows you to express B field as a curl of some vector potential. And this is still true for electrodynamic case, because divergence of B is always 0. And then here in this case, we so in electrostatics, we could write potential in a Laplace equation or Poisson's equation. So Laplacian of V is your source. And similarly, by taking the Coulomb gauge, by choosing the divergence of A to be 0, you were able to do this, right? It's having basically the same Laplace equation, having the same form with the scalar potential keys. And the solutions are the same, of course. And now you are in electrodynamics. Everything can change as a function of time. Electric field changes as a function of time. Magnetic field changes as a function of time. And then in this case, the biggest difference is that electric field, curl of E is non-zero. So you cannot write your solution, your electric field, as a gradient of a scalar potential. It's not possible anymore because you have a B field. It's non-zero. So you have a B field, and then you like B field can be explained like this, can be written like this. So you can express E field as a summation of gradient of V, which is just a static term, plus dA dt, which is a time derivative of the magnetic vector potential. Okay, so you can do that. So then if you take these two, then is there any way to make equation simple? Well, fortunately, you can do that. And here, you can take another gauge, which is called Lorentz gauge. And as I said, divergence of A can be chosen arbitrarily. There's no problem doing that. So here in this case, you choose divergence A to be this, okay, which is called Lorentz gauge. But if you do that, what's happening is that the equation for V and A have the same form if you do that, right? If you look at this, they have the same form. So the only difference here is that if you compare the static case and dynamic case, the difference is that you have this term, this as a new term, the time-dependent term, okay? So instead of you only have a space-dependent, here you have a time-dependent. And then this equation is called wave equations, okay? Why this is called wave equations? Well, we will learn soon. But anyway, this is called wave equations. So what's the solutions? The solutions of these equations can be readily obtained like by doing some change of variable. So if you define t, okay, as a tr as t minus this, and then u here is the 1 over epsilon mu, square root epsilon mu, then this equation just reduces back to this form, okay, and then you can easily obtain the solution, which looks like this. So if you compare this and that solutions, the only difference is that here you don't have any time dependence, but there you have a time dependence, and then the time at the position, the point of interest, at the position of time, point of interest, and the time at the source position are different. So what does that mean? So long story short, if you, well, it's okay even though you do not understand everything here, but like somehow you expand these equations and get to this conclusion, okay? So if you want to calculate V and A at position R and time t, so position R at time t, and then here, of course, the field at this position, so potential and vector potential at this position should be caused by the sources located here, right? And the source position, we use R prime, right? And then another thing that is interesting is that what affects the amount of field, the potential vector and scalar potential here is the source at time tr, not t, and then tr is actually t minus distance between source and the point of interest divided by U. So what does that mean? Anyone can give their interpretation? So let's see, T was now. T is now. Okay. Then because TR is T minus something, TR is actually past. Right? So the source in the past affect the field at this time, right? And then the time difference is defined by this. The actual distance between these two positions divided by U, the speed of light, right? So this actually is tells you about the causality. Okay, causality means 인과율, 인과관계. So, you know, sources are cause, and then fields are outcome, the result. Okay, and then result and the source. If there's a distance between source and result, then there should be time difference, because nothing can be faster than light. So the distance divided by U means the time it takes for light travel from source position to the point of interest, right? So source at this position can affect field at this position after some time, and that time is defined by the light travel time. Okay, so nothing can be transferred faster than light, and then that kind of tells you about the causality, like 인과관계, 인과율. And so this is kind of important thing to note from this relation. Okay, so like in this case, if somebody suddenly changes the source position, or somehow source suddenly disappear, then here this at the measurement position, they know that this source has disappeared after some time, after the light travel time, right? That's what this equation basically tells. And then this reminds you about like special relativity, right? You probably heard about like you know, nothing faster than light, and then you know, the cause and the result have some time difference thing, and then and exactly this the special relativity actually originate from these equations, like electromagnetism. So if you look carefully about the electromagnetism and thinking about coordinate transformation, you can realize that special relativity actually holds. Okay, so is there any question? Okay. And then the final thing is just giving you an exercise. So I said, if you choose the Lorentz gauge, the curl divergence of A to be this, then these two equations and the Maxwell's equation reduces to wave equation. But I did not prove it. So this is just the proof of it. Like if you assume Lorentz gauge, then these two equations holds. I don't want to explain this in detail, so you can just check the lecture note. This is just easy arithmetic manipulation. You can easily check. Okay, so this is it for Maxwell's equations.